Hello and welcome back to Data Science CastNet. In today's video, I thought it would be nice to take a look at the Jet Nemotron paper, Efficient Language Model with Post-Neural Architecture Search, but more specifically to look at the attention block design that they use and to talk more generally about this idea of hybrid architecture language models, right? Where instead of having a regular transformer that has full attention at every layer, you're seeing more and more AI labs and people designing these models adopting something more efficient, whereby you maybe have some layers full attention, some layers sliding window, and also these potential replacements, like linear replacements, like the gated DeltaNet or the new Jet Nemotron block that this paper is going to propose. So we'll look at this paper. We'll also look at the gated delta networks paper. We'll maybe check out briefly this look at a bunch of different linear attention variants. And the reason, well, there's several reasons I wanted to do this now. One is I actually shared this paper with some colleagues a few weeks ago, or this must be a recent update. We definitely looked at it a week or two ago. And so I've been meaning to make a video anyway, but then I saw in a PR to Hugging Face for the Quen Next series of models, they talk about hybrid attention with a combination of gated DeltaNet and gated attention. And high sparsity MOE. So all these moves towards more and more efficient models that can handle longer and longer context without needing, insanely large KV caches and being able to support incredibly high throughput. So the Jet Nemotron paper is a nice one to look at to kind of anchor our discussion and to build some intuition about the things like gated DeltaNet and their modification of it. And I think this is going to be something that you see more and more of as people say, look, we might still want the expressiveness of full attention in some places, but anything we can do to trade that off for efficiency without losing too much performance is going to be a big deal. Okay, so this Jet Nemotron paper, they call this hybrid architecture language models, which match or exceeds the accuracy of leading full attention models, and impressively done without training from scratch. They don't train some new architecture from scratch and show that it does better. They're able to take off-the-shelf existing models and then update them to much higher throughput equivalents through their neural architecture search. And so we'll look at the 3 or 4 key pieces, right? Learning where to replace the full attention, picking which blocks to put in that place, and that's where the gated DeltaNet discussion is going to come in. Designing new blocks, that's their improvements to that. And then hardware-aware hyperparameter search, we don't need to look at much, but it's their final tweaks to squeeze the sort of ultimate performance over the base models. And you can see here, that sort of headline figure, look how much faster we can go. We'll look at sort of a little bit more nuance around that, but also this is a genuinely impressive result. Okay, so here's a kind of key figure overview of the whole process. In a standard transformer, we have an input sequence, right, which gets turned via the embedding matrix into a sequence of hidden states that then go through a number of blocks, and each block has some attention operation and some MLP operation. So the attention is like mixing across the sequence, and then the MLP is refining those representations independently. And then finally, we take the output hidden states of all of those blocks, is usually 20 or 60 or whatever, depending on the size of the network. We feed that through a final projection head that then says what are the probabilities for the what is the expected next token at each position in the sequence. Okay, so step 1 is going to be saying which of the attention layers can we replace with our efficient attention variants. Step 2 is going to be looking at a number of options for that replacement. Step 3 is going to be their improved design based on the one that does best in their tests. And then step 4 is going to be tweaking all of the parameters, the different dimensions and sizes of the different matrices to just ultra optimize the performance on the specific hardware that they're targeting. And so we're going to focus mostly on understanding the intuition for how they choose where to replace and how these gated delta networks work. Okay, so let's skip down to the learning to place full attention. And their observation here is that if we take a network and well, first of all, they train this, they call it a once-for-all super network. They, at every training step, pick a random subset of the attention layers to be replaced with their drop-in replacements, right? So for now, just imagine this is some hybrid attention or efficient linear attention equivalent. At every training step, they're going to pick different layers to choose whether or not they're keeping the original attention and continuing to train that, or they're using their replacement. So that gives us a very flexible end model where now at any inference step or anything we want to test, we can say, okay, let's run a test where we keep we keep everything as the new fast attention alternatives, except for the final attention layer, right? And we can do that for any attention layer index. And so you can then see which attention layer indices really, if we replace that with the linear attention variant, which ones give us a huge drop in performance versus which ones it doesn't really matter if we replace that. And so you can start to find which attention heads are the most important, the sort of useful for these downstream tasks. And the way they're getting this is to, trade out, say, okay, let's use the fast attention alternatives for everything except this layer or for these two layers. And so then this lets them do kind of they call it a beam search, right? Picking the top one or two positions to say, okay, let's keep, attention index 22, and then, okay, now what if we also kept layer 20, right, or layer 24? They can search through that space and pick out their final design, which I think in their cases for these smaller models is something like we keep 2 full attention layers, we have 2 sliding window attention, and then the rest is their gated DeltaNet variant. So very, very clever idea here to train this kind of permutation network where you can pick and choose which layers you're keeping versus which ones you're replacing, and then you can do these downstream experiments to figure out the ideal ones to keep and to replace. Because they do find that completely replacing all the attention layers gives you quite a performance hit, but keeping just 1 or 2 key ones is enough to get back to matching or even improving the accuracy on these downstream benchmarks. Okay, so that's very cool. Not all attention layers contribute equally, only a few critical layers for different tasks. Okay, so now what do we replace those layers with? They consider 6 state-of-the-art linear attention blocks, but then they say, okay, our WKV is a little bit slower, maybe it's not optimized, so they skip it in the rest of the tests. And they find that gated DeltaNet achieves the best overall. And so we'll look at the gated DeltaNet block, and then we'll come back and look at their Jet block, and then we'll talk about the results. In terms of actual performance, I'm not going to go crazy into the numbers. Their models tend to have much higher throughput than the equivalent base model, and match or exceed the accuracy. It is worth noting that they train these models on, I think it's like 350 billion tokens, plus maybe another 50 billion tokens of continued pre-training. This is high quality data, math encoding. This is like NVIDIA's best of the best, cream of the cream pre-training and post-training data. And so you would expect hopefully some improvement potentially just training on that, even if you didn't change the architecture at all. But it's a good way for them to make the point that, look, these new hybrid architectures that we're proposing, they're not hobbling the model. Like, we can still get as good or better performance on all these downstream tasks compared to the model that we started with our much more efficient, much higher throughput, 2,000 or 3,000 tokens per second rather than hundreds of tokens per second. Okay, so let's look at gated DeltaNets. And this is the paper that this builds on. And I'm not going to go into the maths very much. We're going to be very hand-wavy. We'll mostly focus on the diagram, but we just want to build a bit of intuition. So all of these networks are building on something like a recurrent neural network or long-term, short-term memory, LSTM. You have some state, right? So rather than every position in the sequence attending to all past positions in a very computationally expensive step, instead we have this idea of a state that we're carrying along, and at every point we're updating that step, and then when I'm processing a given position, a given token, I can incorporate information from the state, and that's kind of like a proxy for incorporating information from the whole past sequence, but I'm only dealing with this much smaller and more manageable chunk of data. Okay, and so Delta networks, the core idea is that we're taking our state, is the previous state, incorporating the new information, but we're dynamically erasing the value in that state associated with the current key, and then writing some new value, which is the input value, and the old value with some writing strength. Okay, very, very hand-wavy, my apologies. But you can see here the current state is the previous state, mixing in something of the new, like VT and KT are derived from the teeth position, and maybe we should have started with the diagram to see that, with this writing strength beta. Okay, so let's go look at the pretty picture and get more of an intuition for this and what's happening here. So here's our block. We have our hidden state input, and then this is being turned into Q, K, and V with linear projections, and in this case, additional convolution. So taking our input, turning it into Q, K, and V, that's like, oh, very much like regular attention. We have this addition of convolutions here, specific to their design. So this is already incorporating some local information from other positions in the sequence, right? But the convolution is going to be with a small kernel. It's not going to be across the whole. It's not going to be incorporating anything from 2,000 tokens back, but it is some local mixing. There's some normalization, some activation functions. Okay, and then this gated delta rule here is where we'll be mixing in information from the current position with the state to produce the next state, and also produce our output that incorporates information from the previous state. You can see here we're deriving alpha and beta from the hidden state. And so the gated delta rule idea is building on delta networks and saying, let's find the rule here. Our state is going to be our previous hidden state. There's our beta t, right? Like that we were looking at for the DeltaNet. And then this alpha t here is the data-dependent gating term, right? And so having this gating has been around for a little while. I think Mamba 2 had it as well. But in that case, it was dynamic, but it wasn't dependent on the data. And so we're now saying we're going to update our state. And the way we update it is going to be based on an alpha that's like derived from the hidden state that says how much of our previous state should we keep versus how much of the new one, and this beta t as well. So this is like very much a data-dependent update that says how much should we keep, and how do we incorporate that information. In other words, how do we update the state based on the current data? And in this case, it's saying we're going to do that with the hidden state being projected through these two different networks to give us that alpha and that beta, and then that is going to be used when we apply our rule, given the queries, keys, values, etc. Okay, so that's gated delta networks, a way to have a state that represents the sequence up till that point, and then to use that to process our current hidden states, and those hidden states are going to determine what the output of this whole block is, but also how we update that state for the next position in the sequence, and that's going to be these data-dependent values, alpha and beta. So then if we go back to the Jet Nemotron paper, and we look for their modified attention block, it's going to look very similar to that gated DeltaNet version, except that they find we have our input hidden states, we project it to get our queries, keys, and values, right? This WQ is the weight matrix that gives us the queries, the keys, values. They say we actually only need one convolution on the values. We don't need to do convolutions on the queries or the keys. And we're going to make that convolution also dependent on the data. And so this kernel generator here is going to take our input hidden states and produce a convolution kernel for us to use for this step. And then they'll do the time mixing, which is going to look very much like the gated DeltaNet time mixing, and produce their output that way. Okay, so it's a very nice principled block, I think, in that you have the state giving you this like long-term, constantly updated representation of the sequence up until that point. You also have incorporation of like local other positions in the sequence close by via this convolution, and the mixing that happens through that convolution is dependent on the data itself, thanks to the fact that the convolution kernel is generated. The way you update the step, the hidden state, is based on the data as well, right? We're producing our alpha and beta parameters there for that update step from the hidden state. So everything is like any piece of data can decide how it incorporates nearby data via the convolution. It's getting turned into Q, K, and V. It decides how much it updates the step and what update it gets from that state. So it's a very, very cool way to incorporate long distant past, general compressed data from the state, local data from nearby, and then really enrich this representation, which is then going to go through the normal, MLP attention sequence, and just get more and more rich and informative as a hidden state representation. So yeah, that's the attention block. There is more information in the paper if you want to go dig down, like what exactly is the are the different pieces, what are the shapes of the weights. I'd encourage you to like maybe go look for their implementation and play with it if you're very curious. But as a zoomed out point of view, gated DeltaNet or this new Jet block version, you can just think this is something that the complexity here isn't dependent on the sequence length, right? So we've got to apply this operation for every position in the sequence, so there's that scaling. But whenever I'm doing this to process one hidden state, I'm doing the same weight matrix calculations. I'm getting my outputs. There's no then apply that to every position in the past sequence step. Instead, we have a convolution for our local neighborhood, and then we have an interaction with the hidden state, S. And neither of those things are getting any harder for longer sequences. And that's why for much longer sequences, this is able to be so much faster in terms of throughput, because you're not having to keep around all the past KV cache for all the full attention. Instead, you can just take my local, the last, if this is a convolution kernel that's 32 wide, right? I need the last 32 sets of values in a cache, and I need the state, and I'm going to update the state, and I'm going to produce the next token. So it's very, very computationally efficient to just keep adding on to the end of the sequence. Okay, we're not going to talk about the optimization other than to say you can change the dimensions that these are projecting to, right? You can tweak a few little settings of that just to get the absolute max out of your hardware, which in their case I think is NVIDIA H100s and maybe the B200s or something like that. So we're not going to look too much more at this paper, other than let's just skim for final takeaways. The key takeaway being that it works, right? The results are really good, the throughput's really high. The caveat is that A, it was trained on 400 billion tokens of really high quality data, and B, the speed up really shows as your context length gets really long, right? So starting from Qwen 3 and adapting it into Jet Nemotron 2B, at 4K, 8K, and even 16K lengths, very little difference, right? It's only when your context length starts to get really, really long that you're benefiting from not having to deal with, this huge KV cache that you need to keep in memory and these computation expensive operations. Instead, you can just be like very efficiently adding on to the end of the sequence. And so when they say they've got their 53 times speed up, that's decoding given a really long input sequence and then adding on new tokens on the end of that. I guess maybe it was inaccurate to say this speed up is low at these low context. For pre-filling, the speed up is low because you still got to process all of those inputs. But once you've done that pre-filling, continuing to decode is still a lot faster because you're moving less data around and you're just updating basically the last token as you generate. So it is a lot faster even there. My mistake. Okay, zooming out. Very exciting. There's been this long line of hybrid linear attention attempts to completely replace attention, promising, especially like Mamba and these other like state space models, very promising for things like audio and DNA and people building businesses on them, but still somehow like lagging behind full attention transformers and not necessarily seeing huge adoption in terms of the models people actually use. And so really cool to see more and more like improvements and refinements giving more and more expressivity without like trading off all the performance, people figuring out very efficient ways to train these things. That's one thing I didn't go into at all, but very clever design of the kernels and the chunking strategies and the approaches to implement these methods in a way that's not just like theoretically, lower complexity from a computational, like theory side, but in practice as well, just much faster to run on real GPUs, thanks to some very clever math. So it's cool to see people exploring those, testing out a number of them and finding like, oh, okay, these are starting to get really good, right? Like in this case, they found the gated DeltaNet was impressive enough that they then made their modifications and got even better. I'm starting to see real models, Qwen 3 Next series, and a few others, either out or in the pipelines, based on these ideas of saying, look, we might still want a few full attention layers just for the full expressivity that real attention gives us, but these replacements that are so much more efficient, don't need giant KV caches, work really well along contexts. By leveraging those, we can get these hybrid models that are able to do just much faster inference than the full attention equivalent would do, and still be really performant. So I think it's a really neat trend. I think it's worth getting a bit of a familiarity. I know I want to go back in and study these variants and get familiar with how to mess with the state and exactly how the decoding works to give that speed up, and all those other pieces. Just worth keeping an eye on, because I think this idea of these hybrid architecture models is going to just keep getting more and more relevant as people push on that and push on sparsity and push on all the other things they can to get efficient inference. So I hope you found this interesting and not too waffly. We'll see you in the next video.